Hello math friends, this is AP Calculus section 5.2 day 2 notes. Today we are going to continue talking about definite integrals, and we're going to start with some properties of the integral, okay? And as you read through these, hopefully these make sense to you. They should look similar because a lot of them are very similar to like our properties of like limits and things like that we've looked at earlier this year. So first of all, number one, the integral of a constant function from a to b is just going to be equal to the value of the function. And again, a constant function is like a horizontal line. So it's going to be equal to the value of the function. For example, y equals 4. So 4 times the distance along the x-axis, which would be the base of your rectangle, right? So base times height again, or thinking of this in terms of shapes. Number two, the integral from a to b of f of x plus g of x is going to be equal to the integral of f of x plus the integral of g of x, meaning you can break it apart and separate the integrals and then add them together after you integrate. Number three is about constant terms in front of a function, just saying that you can pull the constant term in front of the integral. Number four is similar to number two, except subtraction. The integral from a to b of f of x minus g of x can be calculated by finding the integral from a to b of f of x, finding the integral from a to b of g of x, and then subtracting. And then finally, number five, if you have the same function over like adjacent intervals, so like from a to c and then from c to b of f of x, you can combine those together into a single integral from a to b of f of x. Or likewise, if you wanted to break it apart, you could break it apart so that you could evaluate sections separately. All right, so far in our exploration of integrals and areas under the curve, we have always used rectangles. But if we want to find an exact area, sometimes rectangles aren't the best. And if we take a look at the function today in example 1, which we don't have an actual function for it in terms of like an equation, but we have a graph of it, we can see that they're asking us to find the integral from 0 to 9 of f of x dx. Well, for this particular problem, rectangles don't make any sense because the slopes here are steady, and I could divide this shape, this function, into two triangles, and I can find the exact area under the curve by using two triangles. So what I'm going to do is I'm going to split this up. I'm going to draw a line right here, and I'm going to consider this to be area 1, and I am going to consider this to be area 2. And I know the formula for area of a triangle is 1/2 base times height. So I should be able to calculate those two areas. So my plan here is the area is going to be equal to the value of the integral from 0 to 9 of f of x dx, which is going to be equal to, and again, I'm using that property number 5. I'm splitting this apart into two pieces. I am going to find the integral along the x-axis from 0 to 3 of f of x dx, plus I am going to find the integral from 3 to 9 of f of x dx. So basically, I am just going to be calculating the areas of those two triangles. Well, the area of the pink triangle, 1/2 base times height, so 1/2, the base of that triangle is 3 units long, and the height of that triangle is 3 units long. So 3 times 3 is 9, half of 9 is 4.5. Then I am going to find the area of the blue triangle. So 1/2, the base of the blue triangle is 6 units long, and the height is also 3. So 3 times 6 is 18, half of 18 is 9. And so I get that if I add these two numbers together, 13.5, right? So the answer here is the integral from 0 to 9 of f of x dx is equal to, and this is an exact answer, right? Because of the shape of our function, we were able to find an exact answer for our integral. This is not an estimation. Taking a look at example 2, this time they didn't give us a graph, but that doesn't mean that we can't make one, because if you notice, our function here is linear, right? Our function is 3 minus 2x. So the first thing that I'm going to do, because I'm integrating this from x equals -1 to x equals 2, is I am going to draw a graph of what this function looks like. It is a linear function. We should be able to graph this without any issue. Okay, my y-intercept is 3, and then my slope is -2. So I'm going to go down 2, right 1, down 2, right 1, down 2, right 1. I can also go up 2, left 1. So here's my mostly straight line here. I did my best with the tools that I have. Okay, those are points on my line. And so when I look at my limits of integration, I'm going from x equals -1 to x equals +2. Okay, so basically I have part of my area above the x-axis, and I have part of my area below the x-axis. So my area above the x-axis is going to be this triangle. And then my area below the x-axis is going to be this little triangle right here, okay? So if I write out kind of a formula, again, I'm breaking this interval apart, so I'm using those properties of integrals. So I'm going to say that the integral from -1 to 2 of 3 minus 2x dx is going to be equal to the integral from, and now I need to know where it crosses, and this crosses exactly halfway between 1 and 2, so that crosses at x equals 1.5. So it's going to be from x equals -1 to x equals positive, whoops, that's a +1 there, sorry, I marked the wrong spot. This is 1.5 right here. From x equals -1 to x equals +1.5 of 3 minus 2x dx, plus the integral from x equals 1.5 to x equals 2 of 3 minus 2x dx. And again, the red triangle that I sketched in is going to be a positive area. And, oh, sorry, I need a negative sign right there. The purple triangle that I sketched in is going to be negative because that area is below the x-axis. So when I calculate my areas here, the base of my red triangle is going to be 2.5 units long. So 1/2 times 2.5 times, and the height is 5. And then we're going to have minus the base of the purple triangle, or sorry, 1/2 times the base, which is 0.5, times the height, which is 1. Now notice I put the 1 in front, so I'm going to write this as a +1. I put the negative sign in front, so you don't want a double negative, otherwise you'll negate that. So I could have left it as a adding, and then I would have just called my height of my rectangle -1, but I prefer to just think of it as subtracting the interval that gives you the negative area. All right, so I do the math here, and I get 6.25 plus -0.25. So obviously you add those together and you get 6. So my answer is the integral from -1 to 2 of 3 minus 2x dx is equal to 6. And again, that is an exact value because we were able to break this up into shapes and find the area exactly between the function and the curve because our function was a linear function. So triangles are a very easy way to do that. Example 3 says to rewrite the following as a single integral. So again, using property number 5. Notice that the function is 2x for all 3 integrals. We're going from 2 to 5, and then from 5 to 8, and then from 8 to 13. So we could write this as the single integral from 2 to 13 of 2x dx. And that's all they're asking us to do. Number 4 says, given that the integral from 2 to 4 of f of x dx is 2, the integral from 2 to 8 of f of x dx is 13, find the integral from 4 to 8 of f of x dx. Well, we can begin with the fact that if we want the integral from 4 to 8 of f of x dx, that should be equal to the integral from 2 to 8 of f of x dx minus the integral from 2 to 4 of f of x dx. Just basic subtraction, right? And since they gave us these values, we know that this is 13 minus 2. So our answer is the integral from 4 to 8 of f of x dx is going to be equal to 11.